Hello and welcome everyone to the 8th week of interactive live sessions for the course on Computational Fluid Dynamics for Incompressible Flows. This course is being offered by NPTEL and is being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering in IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras and I am the TA for this course. Like every other week, this week also we shall be solving some problems together and discussing any questions or doubts that you may have related to the course. These are interactive sessions, so let's make sure that the interactions are maximum. Anything related to the course that you may have on your mind, please don't hesitate to ask. Okay, and with that, and no further ado, we will start digging into today's questions. So let's start with question number one of today's session. So as we know, in week 8, our topic of discussion was the stream function vorticity formulation of uh, fluid flows. Now, why even do that? So that's related. That's the first thing which should come into our minds, that we already have the governing equations for fluid flow, which are the continuity equation and the momentum equations, momentum conservation equations, which together are known as the Navier-Stokes equations. So why even formulate this in a different way? Of course, there are several advantages to it. The first question is related to that. So question number one is asking us, what is the primary purpose of using the stream function vorticity formulation in computational fluid dynamics or CFD? So there are four options given below. Read them carefully, and once you have figured out the correct answer, you can either type in the chat box or you can unmute and answer as well. It's really up to you. So read the question carefully. The question says, what is the primary purpose of using stream function vorticity formulation in computational fluid dynamics? Is it option A, to simplify the Navier-Stokes equations? Is it option B, to improve numerical stability? Is it option C, to conserve mass and momentum? Or is it option D, to reduce the computational time? We have one response in favor of option A. Sorry. Okay, so we have one response in favor of option A, another one in favor of B. So let's have a look at the solution. The answer is actually option A, to simplify the Navier-Stokes equations. So what actually happens in, let's say we have a 2D flow field. So there, what are our equations? The continuity equation, dou u, dou x plus dou u plus dou v dou y equal to 0, the continuity equation, and then we have the x momentum equation, which is u dou u dou x plus v dou u dou y equal to minus 1 by rho into dou p dou x, plus we have the diffusion term, which is mu into nu into dou to u dou x squared plus dou to u dou y squared. Similarly, we have the y momentum equation, which is u dou v dou x plus v dou v dou y equal to minus 1 by rho dou p dou y plus nu into dou square v by dou x squared plus dou square v by dou y squared. Now we have three equations and three unknowns over here. The unknowns are u, v and p. Now when we simplify this down to stream function vorticity formulation, then we have only two equations, which are, the Laplacian of the stream function being equal to negative of the vorticity and the vorticity transport equation. So in the unsteady case, we have dou omega dou t, we can plus we have the vorticity, uh, you know, the convection term, that is uh, u dou omega dou x plus v dou omega dou y equal to the diffusion term, nu into dou square omega dou x square plus dou square omega dou y square. Now look at the difference between these two. Here we had three equations and three unknowns. And here we have two equations and two unknowns. So it greatly simplified down the original Navier-Stokes equations. So this is more easier to calculate and solve using a digital computer. So it greatly reduces our load. So this is one of the primary purpose of using a stream function vorticity formulation over the velocity pressure formulation, which is the conventional Navier-Stokes equations. So that's why option A would be the correct answer. Does that make things clear? As to why or how does it simplify. So this is how it simplifies. Instead of solving for three equations and three unknowns, we are now solving for only two equations and two unknowns. Okay, to be noted here, I wrote down u and v over here, but these also would be expressed in terms of the stream function, right? So it's not u or v. You can say that, sir, these unknowns still remain, but no. The main unknown here is psi and omega only. So the two unknowns are psi and omega. Okay, I hope things are clear. So we will move on. We will move on to question number 2 of today's session, which is asking us what is the relationship between streamlines and the stream function in a two-dimensional flow field. Is it option A, streamlines are perpendicular to the stream function? Option B, streamlines are tangent to the stream function? Option C, streamlines are parallel to the stream function? Or option D, there is no relationship between streamlines and stream function? So read the question carefully, and once you have figured out the solution, you can either type in the chat box or you can unmute and answer as well. So what is the relationship between streamlines and stream function in a two-dimensional flow field? We have one answer in favor of option B. Let's see if we get more responses. So there are four options given here. Option A, streamlines are perpendicular to the stream function. Streamlines are tangent to the stream function. Streamlines are parallel to the stream function. Or there is no relationship between streamlines and stream function. So what I mean by stream function here are lines of constant stream function. So it could be something like psi equal to c, where c is a constant. It's some number, 1, 2, 10, 10,000, like that. So what is the relationship between them? Option A, perpendicular. Option B, tangent. Option C, parallel. Or option D, there is no relationship in between them. Okay, we have another response also in favor of option B. So we will go ahead and look at the correct solution. The solution is actually option C. Streamlines are parallel to the stream function. So the thing is, let's say we have a field like this, and Let's say I draw some lines of constant psi. Let's say this is psi equal to from psi 1, psi equal to psi 2, psi equal to psi 3. These are constant stream function lines, and streamlines are so in a way I can understand why you guys chose streamlines are tangent. So the velocity at all points are tangents to the streamline. So that might have been the source of the confusion. But streamlines and stream functions, they are actually parallel. So streamlines are nothing but the lines of constant stream function value. So a stream function would actually overlap with this. So they would be parallel to the lines of constant stream function. They are one and the same thing. They are not anything different. So the correct answer would be option C, that stream lines are parallel to the stream function. Hopefully that is making sense, right? If you have any need of clarification, please ask. I hope that I'm making sense here. So the thing is, streamlines and lines of constant stream function, they are basically the same thing. So they would be parallel to each other, right? Okay. So I hope that makes things clear, and we will move on. We will move along to question number 3 of today's session, which is asking us, in the stream function vorticity formulation, what does the vorticity represent? Is it option A, the rate of change of velocity? Is it option B, the curl of the velocity field? Or option C, the divergence of the velocity field? Or option D, the magnitude of the velocity field? So, the topic of today's focus is stream function vorticity formulation, and one of the primary things over there are the stream function and the vorticity. So now vorticity is what we are looking at now. What does it actually represent? Does it represent the rate of change of velocity? Does it represent the curl of the velocity field? Does it represent the divergence of the velocity field or the magnitude of the velocity field? So rate of change of velocity would be, okay, we have one response in favor of option C. Let's see if we get more responses. Read the question carefully and try to pick out the correct solution from the options given here. In the stream function vorticity formulation, what does the vorticity represent? Is it option A, the rate of change of velocity? Is it option B, the curl of the velocity field? Is it option C, the divergence of the velocity field? Or is it option D, the magnitude of the velocity field? Okay, so another response is curl, so I'll assume that is option B. Okay, so we have one response in favor of option B, the curl of the velocity field, and one in favor of option C, the divergence of the velocity field. Let's have a look at the correct solution. So the solution is actually option B, the curl of the velocity field. So if we look at each of them, the rate of change of velocity is nothing but, some dou u dou t. The curl of the velocity field is del cross u. The divergence would be del u and del dot u, and the magnitude would be simply, the modulus of u. So it's actually the curl that represents vorticity. So we define omega as the curl of the velocity. So in two dimensions, we only care about the z component of vorticity, and we have only the x and y components of u over here. So if we write it down this way, so we have dou u dou y minus dou v dou z, dou v dou x. Okay, let me make sure I did this correctly. So we have, x cap, y cap, z cap, dou dou x, dou dou y, dou dou z, and the components of velocity. So in our case, we have no z component, so we will only have the z component of the omega. So omega vector would be dou v dou x, dou v dou x minus dou u dou y, right? And this would be in the z cap direction. So I did this incorrectly. Let me fix it. So we have dou v dou x minus dou u dou y. That is the curl of the velocity field. That is what vorticity represents, right? Not the divergence. Okay, I hope that makes things clear. If you have any questions, you can ask. Right, so if there are no questions, we will move on to the fourth question of today's session. So the fourth question is asking us, what is the mathematical equation that relates the stream function to the velocity field in a two-dimensional flow? Is it option A, u equal to dou psi dou y and v equal to minus dou psi dou x? Or is it option B, u equal to dou psi dou x and v equal to minus dou psi dou y? Or is it option C, u equal to dou v dou y and v equal to minus dou u dou x? Or is it option D, u equal to dou u dou x and v equal to minus dou u dou y? Okay, so we have one response in favor of option A. Let's see if we get more responses. Read the question carefully and the options carefully. It's a very simple question related to the mathematical definition of a stream function. So what is the mathematical equation that relates the stream function to the velocity field in a two-dimensional flow? Is it option A, u equal to dou psi dou y and v equal to minus dou psi dou x? Is it option B, u equal to dou psi dou x and v equal to minus dou psi dou y? Is it option C, u equal to dou v dou y and v equal to minus dou u dou x? Or is it option D, u equal to dou u dou x and v equal to minus dou u dou y? So let's have a look at the correct solution. It is indeed option A, that is u equal to dou psi dou y and v equal to minus dou psi dou x. Now the opposite convention is also used in some books, like this would be negative and this would be positive, but it's a matter of convention only. Otherwise, everything is same. Like uh, so, what it actually helps us to do, let's say in case we have an incompressible flow, so we have dou u dou x plus dou v dou y equal to 0 being our continuity equation. So if we plug in the values of u and v in terms of the stream function, then what we get is, say, dou x of dou psi dou y, plus we have here dou y of minus dou psi dou x. So we have dou 2 psi dou x dou y plus dou 2 psi, sorry, a negative sign would come here. So we have a negative dou 2 psi. So we can define one field variable psi, which is a function of both x and y, uh, that by default satisfies the continuity equation, and that's a very important property to have, right? So this is why stream function is a very crucial parameter that is studied in fluid dynamics. And how is it defined? It is defined as shown in option A, as u equal to dou psi dou y and v equal to minus dou psi dou x. Clear? Okay. So we will keep moving along. We will move on to question number 5 of today's session. So question number 5 is asking us, how is the vorticity calculated in the stream function vorticity formulation? Is it done by option A, by taking the gradient of stream function? Option B, by taking curl of the velocity field? Option C, by taking divergence of the velocity field? Or is it option D, by taking the Laplacian of the stream function? So if I write down each option in detail, so the first one, by taking gradient of the stream function. So vorticity equal to gradient of stream function. Option B, by taking curl of the velocity field. So u equal to curl of omega equal to curl of u. Option C, by taking divergence of the velocity field. Or option D, by taking Laplacian of the stream function. So which way is vorticity calculated in stream function vorticity formulation that we're focusing on this week? Is it by option A, by taking the gradient of the stream function? Is it option B, by taking curl of the velocity field? Is it option C, by taking divergence of the velocity field? Or is it option D, by taking Laplacian of the stream function? So we have one response in favor of option A, that is this one. Omega equal to grad of grad of psi. Let's see if we get more responses. Okay, so in second response in favor of option B, that is by taking uh, omega equal to curl of u, or del cross u. So let's have a look at the solution. The solution is actually option D, that is by taking the Laplacian of the stream function. So let's go back here. So first of all, this option A itself, this mathematical form itself is incorrect. Sorry, the mathematical form here itself is incorrect, and option B mathematically is fine. Vorticity is defined that way, but in stream function vorticity formulation, we don't deal with u anymore. We deal with only omega and psi, and one of the equations that we solve there is this omega equal to grad square psi. So where do we get this from? We get from this equation only. So let's go to the solution. So omega can be written as the curl of u, and u itself uh, is defined as, or let's say, how to write this down more accurately. Okay, so we will do this for the 2D case. So omega is equal to dou v dou x minus dou u dou y, and u, as we know, is dou psi dou y, and v is minus dou psi dou x. So we will simply plug in these in the first equation. So then we will get omega equal to dou x. Instead of v, we will write down this. So dou psi dou x, and minus dou y of u. Instead of u, we will write down this, dou psi dou y, and this would give us omega equal to minus del square psi dou x square minus dou square psi dou y square, which is nothing but the Laplacian. So I'll take the negative sign in this side, so it will be minus w minus omega equal to del square psi, or the Laplacian of psi. So that's why option D would be the correct answer. Does that make sense? Okay. So we will move along. We will move along to question number 6 of today's session, which is asking us, how does the stream function vorticity formulation handle boundary conditions? Option A, it automatically satisfies all boundary conditions. Option B, it requires additional boundary conditions beyond those for the velocity field. Is it option C, it does not require any boundary conditions? Or is it option D, it only requires boundary conditions for the vorticity field? So read the question carefully and try to figure out the correct answer. How does the stream function vorticity formulation handle boundary conditions? Option A, it automatically satisfies all boundary conditions. Option B, it requires additional boundary conditions beyond those for the velocity field. Option C, it does not require any boundary conditions. Or is it option D, it only requires boundary conditions for the vorticity field? Which one would it be? Okay, so we have a response in favor of option C. It does not require any boundary conditions. So if you look at the solution, the correct solution would be option B, that is, it requires additional boundary conditions beyond those for the velocity field. So let's go back to the two examples that we saw in the lecture. So one was that of a lid driven cavity, and the other one was that of a flow in a channel. So in both cases, we needed boundary conditions for both psi as well as omega, that is stream function, and as well as vorticity. So it's not that we do not require any boundary conditions or that it is automatically satisfies all boundary conditions. We need to specifically define the boundary conditions of the stream function and the vorticity at the boundaries. So we need additional boundary conditions beyond those for the velocity field. So only u and v boundary conditions are not sufficient. We need those for the stream function and the vorticity as well. Both can be determined if we know the u and v, but they have to be determined. That is necessary. Does that clear things up? Okay. So if you have any questions, please stop me and ask. Okay. No need to hesitate, or don't hold on to doubts or some questions which you may have. Anything related to the course, you can freely ask over here. Okay. So we will move along. We will move on to question number 7, which is asking us how is pressure calculated in stream function vorticity formulation? Is it by option A by using Bernoulli's equation, option B by using pressure Poisson equation, uh, is it option C by using Euler's equation, or is it option D pressure cannot be calculated in stream function vorticity formulation? So it won't be equation here, but formulation. So if we need to know the pressure in the velocity field, so where is pressure required? Let's say we have, an aerofoil like this, and we have some flow around it. So we need the pressure at all points of the boundary in order to calculate the drag and the lift force. So to calculate the drag and lift, we need the pressure in at all points of the boundary. Now, if we are using a stream function vorticity formulation, which kind of neglects pressure upfront, uh, not neglects, it avoids it. So, if we need it, how do we calculate that? Do we do that by Bernoulli's equation, by using pressure Poisson equation, by using Euler's equation, or option D, pressure cannot be calculated in this formulation at all? So the answer is in favor of option B by using pressure Poisson equation, and it is indeed correct. So what is done is, uh, let's say we have the two x momentum and y momentum equations to begin with, right? So we had dou u dou x plus v dou u dou y equal to minus 1 by rho dou p dou x plus, I'm writing this in shorthand, Laplacian of u, and similarly we had, okay, this also I'll write it in shorthand just to do things quickly. So p dou y plus nu into Laplacian of v. Now what is done is that, let's say if this is equation 1 and this is equation 2, uh, dou x of 1 plus dou y of 2 is done, and both are added. So that, and then further simplification would, and another step would be to convert these u's and v's in terms of the stream function. That would finally give us a Laplacian of p being equal to rho into, uh, so it will be u square. So dou psi dou x whole square, dou psi dou x into dou psi dou y minus dou to psi dou x dou y whole square. This kind of an equation. So this is known as a pressure Poisson equation. So once we have solved using stream function vorticity formulation, we already know this psi field, the field of the stream function. So from there we can calculate these gradients and plug into this equation, and by solving this Poisson equation in pressure, we will get the pressure field as well. So anywhere we need to know the pressure, we can find out using this. Okay. So that's how pressure is calculated in stream function vorticity formulation. I hope that makes things clear. We will move on. We'll move on to question number 8 of today's session, which is asking us, can the stream function vorticity formulation be used for three-dimensional flow fields? Option A, yes, but it requires the use of vector calculus to formulate the equations. Option B, also yes, but the reason is different. It says yes, but it is a more general formulation that can be used for both 2D and 3D flows. Option C says no, it is only valid for certain types of flow fields, such as laminar or steady state flows. Option D says no, it can be used for two-dimensional flow fields only. So among the four options, two say yes and two say no. But then also the reason for yes or the reason for no is important. So make sure you pick the correct option after reading the entire thing carefully. So we have a response in favor of option B. Yes, it is a more general formulation that can be used for both 2D and 3D flows. Let's have a look at the solution. It is actually option A. Yes, but it requires the use of vector calculus to formulate the equations. Now, whatever we did for 2D flows was pretty simple and straightforward, but in 3D things gets complicated. So what were the two equations which we had? One was, you know, the in 2D we had minus of omega equal to Laplacian of psi. This breaks down in 3D. So this is what we can't do. And the another equation was the vorticity transport equation. So we had omega dot E plus, sorry. Uh, so we had equal to nu into grad square omega, del square omega, sorry. Now in 3D we cannot do all this. So in 3D we have three components of uh, vorticity. So we will have something like x cap, y cap, z cap, dou x, dou y, dou z, and we have three components of velocity which can be written as, okay, so we have three components of velocity over here, ux, uy and uz, let's say, or I'll write them as u, v and w, and the stream function itself is defined in a manner that okay, so let me try to remember how is stream function done here. Yeah, so stream function can be written as, dou psi, or d of psi can be written as dou psi x cap plus dou psi y cap plus dou psi z cap, and that has to be uh, parallel to the that has to be tangent, the velocity has to be tangent to this dou psi at all times. So we will have something like these will be dou psi x, dou psi y, dou psi z. So it would have three components. So we will have something like dou psi by u would be equal to dou psi y by v equal to dou psi z by omega w. So using this equation and this equation, we will get, three components of omega and three components of vorticity. So three components of stream function and three components of vorticity. So that itself is a very complicated way to do things, and more importantly, the main reason which we why we did stream function vorticity formulation, that instead of three equations and three unknowns for 2D, so in 3D it would be four equations and four unknowns. This is for velocity pressure formulation in 3D. From here, we will go to six equations and six unknowns. The six unknowns being the three components of stream function and the three components of vorticity. So this is in stream function vorticity formulation. So instead of simplifying, we made things more complicated in 3D. So that's why in 3D flow fields, this stream function vorticity formulation doesn't really find much of an application. It is more useful in two-dimensional flow fields. So, but nonetheless, it can be applied for three-dimensional flow fields, but we have to make use of vector calculus to formulate the equations. But ultimately it makes things more complicated, as you can see. Do I make sense? Okay. So if everything is clear up until this point, we will move on to question 9 of today's session. So question 9 is asking us, which dimensionless number appears in the non-dimensionalized form of the stream function vorticity equations? Is it option A, Prandtl number? Is it option B, Courant number? Is it option C, the Struhal number? Or is it option D, the Reynolds number? So if we non-dimensionalize the stream function vorticity equations, uh, one non-dimensional group shows up. Which group is that? Is it Prandtl number, Courant number, Struhal number, or Reynolds number? Which dimensionless number appears in the non-dimensionalized form of the stream function vorticity equations? Is it option A, Prandtl number? Is it option B, Courant number? Is it option C, Struhal number? Or is it option D, Reynolds number? Okay, so we have a response in favor of option B. Let's have a look at the solution. The solution is actually option D, the Reynolds number. So starting from the equation which we had for vorticity transport. So we had, you know, u we had u dou omega dou x plus v dou omega dou y equal to minus equal to mu into dou square omega dou x square plus dou square omega dou y square. Now, if we non-dimensionalize each of these terms, so let's say, and we will take our velocity scale as the flow velocity u and the length scale as the characteristic length L. Now, using these, if we non-dimensionalize all these equations, so the final form would be u star dou omega star. Okay, let me determine them. So define them. So u star is u by capital U, x star is x by L, y star is y by L. Similarly, uh, omega would be, sorry, omega star would be, let me write it down here. So omega star would be omega into uh, L by U. Right? I hope this matches dimensionally. So that is per second per second. Yeah. So if we use this kind of a scaling, so the final non-dimensionalized form that we will get is something that looks like this. And in the left hand side, we will get 1 over RE as the non-dimensional grouping. So it basically comes as nu over UL, right? So which is nothing but 1 over RE, which is the Reynolds number. So the Reynolds number is the non-dimensional group that shows up when we write down the stream function vorticity equation in their non-dimensional form or dimensionless form, right? Okay, so moving on, we will move on to last question of today's session, which is asking us that for two-dimensional incompressible flows, vorticity stream function formulation is more accurate than velocity pressure formulations. So this is a statement that we have here. Now, is that statement true or false? For 2D incompressible flows, vorticity stream function formulation is more accurate than velocity pressure formulations. So we have a response in favor of option A, true. Can you say why? The correct answer is true. It is actually more accurate, but why is it so? Any guesses?
Sir, in vorticity stream function method, I think we can consider this lines to be streamlined. I think so. I'm not that sure.
Lines to be straight lines. Which lines?
I think streamlines.
Sorry, I'm not getting it.
Is it the streamlines? I think it's the
Streamline.
straight. Yeah.
Not really. The streamline would be along the velocity. If there is a complex flow field, then it doesn't has to be straight line. So the actual reason it is more accurate. So how do we quantify accuracy? So we had the we discretize the system into delta x and delta y and so on, right? Delta t, and we define the order of accuracy as some delta x or delta x square and so on. So now what happens in velocity pressure formulation, we are dealing with uv themselves, and depending upon whether we are using the central difference or forward difference or backward difference, we have some order of accuracy in delta x. So let's say I'll call this n. So let's say we have something of the nth order. N can be 1, 2, 3, whatever, depending on the discretization scheme you're using. If you use the same discretization scheme while we are in the vorticity stream function formulation, where we have psi and omega, and these are actually gradients of u. So we have either dou x or dou v dou y or dou u dou y or dou v dou x, gradients of u and v. So here, even if the the order, if we use the same discretization scheme, we will get another added order of accuracy over here, since we are dealing with gradients, right? So what actually happens? So let's say if we expand this out into some Taylor series or something. So we have, so earlier in velocity pressure formulation, we had some u at I plus 1 is equal to u at I plus delta x into dou u dou x plus delta x square by 2 factorial plus this second gradient, second derivative, and so on. A series like this. We have the similar thing over here. But the catch over here is that psi itself is gradient of u, right? At I plus 1. So now if we integrate this and try to look into it, we will see that the higher order term is actually lower, or the leading truncation term is actually one order higher than that we would have gotten using velocity pressure formulation. So we have a added order of accuracy. So that's why they are more accurate than velocity pressure formulations if we use the same discretization scheme for both. Make sense? Okay. So that's all for today from my side. If you have any questions, you can ask.
Sir, in the previous question, ninth question, there was a number called the Strouhal number.
Yeah.
Actually, what it represents? The third one, C. Yeah.
Small number is actually, as if there is, let's say, some vortex shedding, we have a cylinder like this, we have a flow incoming, and we have a von Karman vortex street like this, and there is some periodicity to the problem. There is a frequency f, which is given in hertz. So let's say per unit time there is this many vortices being shed. So the Struwell number is determined as in this way. So we have frequency over here, and what was that? L by U, was it? No, U by L. So frequency, yeah. So let's say we have the diameter of this as L, which is the characteristic length, the incoming velocity as U, and the frequency in which these vortices are being shed as F, then the Struhal number would be given as FL by U. Does
Sir,
that
actually, what is the significance of that number?
significance? So this is basically, you know, let's say how do we define significance of Reynolds number? That is the ratio of the inertial forces to the viscous forces. Similarly, the Struhal number is basically the ratio of two time scales. So on the top we have F. So this can also be written like this. We have F divided, or in this way. So in the denominator we have 1 by F, and in the numerator we have L over U, right? So this can be simplified into this form. So if we look into this form, the numerator L over U is the flow time scale, and 1 by f. What is 1 by f? 1 by f is the time p one. So f is actually 1 over t, and t is 1 over f. T is nothing but the time period of two vortices being shed. So one vortex left after a time capital T seconds, the second vortex would be shed. So this is that vortex shedding time scale, or any periodic time scale associated with the system. So we have a system time scale in the denominator. So the ratio between these two is the Struhal number. Does that answer your question?
Yes, sir. Thank you.
Okay. So if
Sir,
there are yeah,
one more thing, sir.
yeah, sure.
So, what will be the usual value? Is it less than one, or is there any criteria less?
It could be anything. That depends on the system itself. There are various ranges of Struhal numbers in which flow fields are observed in both industry as well as in research.
Oh, okay, sir.
So it depends on the configuration. It could be very low Struhal number, in which case the Struhal number is neglected. That is, the dynamic effects of the flow field is actually neglected, and a steady state formulation is done. In other cases, when Struhal number is close to 1 or greater than 1, then these dynamic effects are important, and then we have to do an unsteady analysis of it. So in that case, the dou u, dou t, dou omega, dou t, the transient terms, they become important. So in this simple case only you can see. So let's say if we have a frequency very low, then which means the Struhal number is very low. Something like one vortex is being shed, and then after a very long period of time, the second vortex is being shed. So the time in between, that can be solved as a steady flow only. So in that case, the unsteady effects becomes less important. But let's say we have a very frequent vortex shedding, one vortex, another vortex after that, in a very frequent consequential manner. If vortices are being shed, then f would be large and Struhal number would be large, and in that case the unsteady effects are important. Okay, I hope that answers your question.
Yes,
Anything
sir.
else?
It's all. No, sir. It's fine.
Okay, so we had a great session today. Thanks for joining, and see you next week.
Thank you, sir.